This video is all about Big O. It's a concept critical to algorithms and the most mathematical we'll get in this course. In interviews, you'll often be expected to estimate the Big O of a problem that you solve. I was very careful when making this video because unless you understand Big O from first principles, that is at the lowest level, how does it work, then what you end up doing is just memorizing Big O for different problems. This is not good for two reasons. First, if you get a problem that you haven't seen before, which can happen even if you do hundreds and hundreds of problems, you can get that one you didn't do. Well, then you're going to have no idea how to get the Big O. And the other reason is this. Think about high school math where you got partial credit if you showed your work. Well, by showing your work on getting the Big O, instead of getting partial credit, you can get more like 80 or 90% credit, even if you don't get the exact answer right. The reality is the whole point of the programming interview is to shed light on your problem-solving abilities. So what do you think does that better? Breaking down your algorithm and explaining step by step what you think your Big O might be, or just spitting out the correct answer with no explanation? I'll let you think about that one. So let's get into what Big O actually is. Big O represents the efficiency of your algorithm, and there are two different types of Big O. First, there's time, which is related to performance. Fast equals efficient, and efficiency is everything in code. Space is related to memory. How much extra space, meaning variables or data structures, do we need to solve this algorithm? So in reality, if you have large inputs for your functions, both time and space can start to cause problems, hence their relevance. We also use these as a benchmark to compare different algorithms, measuring how good they are. For example, there's a bunch of different ways to code sort, and they all have different efficiencies. Basically, it's like giving them a grade in school. Now, how exactly do we assign this grade? Well, we measure it not in absolute terms, but in relative terms, relative to the size of the input. Just think of an input as an argument to a function. Now, if we double the size of this input, do the time and space scale proportionally? Do they scale slightly less, or do they scale slightly more? What do you think? Let's break it down with an example. Let's create a function called length, which measures the length of an array or list. We can pass in an input of size 3 and say that it takes 1 full second to complete. Pretty bad, but it's just an example. Then I pass in an array of size 6 and it takes 2 full seconds to complete. Now, when we compare these two inputs and their times, we can notice that doubling the input size also doubles the time it takes. We call a proportional exact increase like this linear time. We could also say the relationship between time and input is 1-to-1. And written in Big O notation, we call linear time O of n, and we write it as a Big O with an n in parentheses. Let's also say for this problem, we did not use any extra space. Now, extra space, of course, does not include the size of our input. So we start and end with 0 space. If either the space or the time has no relationship with the input, then we call this constant space. And in Big O notation, constant space is O of 1. These terms, linear, constant, and there are a few more, we can also refer to as order, with each being a different tier of efficiency. So here's a short tier list that goes from most efficient, or shortest time or least space, to the least efficient. Now, I could give you an example for each one now, but I think it's better to wait until we get into algorithm-specific videos because we are going to cover this entire spectrum within our algorithms. We skipped a few steps ahead with that explanation, but let's boil it all the way down to get to the essence of what Big O actually is. Let's bring back our length function, but this time, look at the code that's inside. Now, if we think about what this code actually looks like, it's probably something like this. We have a counter variable and a loop that is just incrementing the counter on each step. The truth is, every single line of code has its own time complexity. But there's a little trick you can use to get each line's time complexity quickly. Simply ask the question, how does the input size, whether that's string length or array length, affect this specific line? If the answer is it doesn't have a direct impact, then by default, that line is constant time because it has no relationship to the input. Looking at our first line here, creating that counter variable is going to happen whether we pass in 1 or 100 array items. So by default, this line is constant time. Now the real question is the counter variable constant space, or does this variable scale with the size of our input? You might think, yeah, it does because we're incrementing the counter up to the length of our input. But the truth is, integers always take up the same amount of space unless they're really, really, really big. Look up 32 and 64-bit integers if you want to read more about that. But the TLDR is we use a constant amount of space regardless of the integer value. So the time and space for the first line is going to be constant. You might be thinking that took forever to do one line, but if you practice doing this for every line, things like a counter being constant space, you're going to see that over and over again. Now, when we look at our loop, well, clearly this is going to run n times proportional to the size of our input. So there is a direct relationship between our input and the time of this code right here. Then what is the relationship? Well, simply look at two different inputs. Simple as possible is always the best way to go. So array of size 1, array of size 2. We're going from size 1 to size 2, 1 iteration to 2 iterations. So clearly there is a one-to-one relationship, linear. So that's the general framework, but you might be saying, okay, that covers constant and linear, but what about the other 5 or so? Well, no worries. We're going to cover all of these in algorithm-specific videos, going through line by line, and I'll give you some shortcuts or things you can look for to quickly get the time complexity. So looking at our time complexity, we don't just have O of n, we have O of 1 and then O of n. So we can really say that it's taking O of 1 time plus O of n time. So even in this very simple function, we have multiple terms. And if we had a long function, I hope you can see how this time complexity would get pretty out of hand. We just have O of 1, O of 1, O of 1, O of n, O of whatever. And that's not really a useful format. So what we end up doing is needing to simplify. And we do that by only keeping the terms that are in the highest order. So here we have O of 1 and O of n. But we will end up dropping the O of 1 because compared to the O of n, it doesn't even matter. Since each tier of big O is an order or an order of magnitude larger than the last, when we get to larger size inputs, the lower order terms become completely irrelevant. In this example, it's very clear that if we had an input size of 500, well, that little variable creation would not be relevant to 500 loop iterations. But even if I had an n squared or quadratic time complexity next to an n and also use that 500, well, you can see that next to the n squared, the n is totally irrelevant. Okay, so we know we drop the lower order terms. And to simplify further, we often drop the constant terms as well. Let's say we have two loops next to each other. They're O of n and then O of n, so n plus n, so 2n. So in practice, you can actually just drop that 2 entirely, because at the end of the day, all we really care about is the order. The difference between the orders is so great that even if we double or quadruple or times 10 linear time, then at large inputs, let's say 5,000, it's really not going to matter when we compare orders to each other. So that's how we simplify big O. So the length function we just did is a nice clean example because we always increment the counter n times, one for each iteration of the loop. But in most cases, functions have a range of efficiency instead of an exact efficiency every time. Let me explain that with another example. Let's use the index or the index of function, depending what language you're using. So what this function is doing is searching a string for a character, and then if we find that character, it's returning its index. In considering the big O, we have to train ourselves to think about the entire spectrum of possibilities here. More specifically, what is the best case or the least amount of effort, and then what is the worst case? Now in reality, the index function is not magic. It's looking at one character at a time and seeing if it matches our input character. So considering the spectrum here, the best case would be the character we're looking for is the first one we look at. Now let's assume that this function is just scanning from left to right. So it's using a loop to look at each one of the characters in the string and testing each one to see if it matches. Now, if the character we're looking for is the first one, then it will instantly return because we'll run the first iteration of the loop, it'll match, and then the loop will break. But on the other end of the spectrum, if the character we're looking for is not in the string at all, then we're going to have to individually check every character before knowing that it's not in there. So for this string, we would need 5 ticks or 5 equality checks, which is equivalent to the size of our input. And this is what we call our worst case. So our best case is going to be O of 1 or a single check operation. But our worst case is going to be O of n or proportional to the length of our string. With big O, it's the convention to always take the worst case. So we can say that this index function is O of n or linear time or the order of n. Alright, those are the basics, and we are going to dive a lot more into big O in each specific problem. But your takeaways from this video should be the following. First, every line of code has a big O time complexity, and every variable we create has a space complexity. Now, instead of manually adding together every line's time complexity, what we do instead is simplify by taking only the highest order or least efficient term. And you can do this quickly by scanning through, looking for things like loops, sorting, and other stuff that we'll get into soon. We also simplify by dropping any constant, so if we have O of 5 or 3n, we just drop that constant term to be more clear about what order we are in, because that's what we care about. And finally, when we consider our entire spectrum of possible inputs, we always have to think about the worst case. The best example is anything when we're searching. We could be lucky and find what we're looking for on the first check, but worst case, we will have to check all the items that we're looking through. Now, there are ways around this with clever search algorithms that we'll get into, but understanding big O allows us to understand why they are more efficient. All that said, we're going to talk about time and space complexity at the end of each algorithm video. And we're going to get into that first algorithm video right now. So there's a lot to look forward to. Let's go.